Hey everyone, this is the third time I made this video. Fingers crossed it works this time. We are going to be introducing a lab that we're going to be doing a little bit later. Actually, I think I'm posting it on the same assignment. We'll be relating it to Target 7.1. I'll be teaching you a few new terms, a little bit of math and stuff like that. Let's get to it. All right, so let's just sort of quickly review what we have been working on. We have been doing projectile motion. So if we, for example, one we're going to be using all day is we're going to shoot a cannon. So say we have some cannon, very artfully drawn, and this cannon shoots, a cannonball. This cannonball will fly out of the tube here, and it'll have some velocity. And the cool thing that we've noticed, and that we've been using to our advantage, is that this velocity is partially horizontal and it's partially vertical. But the horizontal part doesn't change, while the vertical one does. Well, why doesn't it change? Because the acceleration in the vertical is -10 meters per second squared. So our vertical stuff will be changing, but the horizontal acceleration is 0. There is no force causing it to accelerate. Remember, all accelerations come from unbalanced forces, and there is no unbalanced force. The only force we have acting on the ball once it's in the air here is the force of gravity. So consequently, our ball just follows this path right here, this nice little parabola. And every time, the horizontal velocity stays the same, while the vertical velocity gets more and more negative. So that's projectile motion in a nutshell. I'm hoping you've been successful at it. Now, if you are not there yet, stop this video. It's okay. Come back to it in a few days. Heck, come back to it Friday after you've gotten your first projectile one done and you feel good about it. But for now, if you are okay on projectile motion, if you feel ready to move on, well, let's do it. So there's a few things we have to note. The Earth is not flat, is it? The Earth is a nice, pretty suit, not oval, nice, pretty circle. Now, that does a few weird things. You know how we said our force of gravity was down? Well, yeah, where we're at, the force of gravity is down. But what about over here? The force of gravity is that way, down is that direction, or that direction, or that direction. Everywhere on the surface of this Earth has a slightly different direction for the force of gravity. Now, it probably won't affect us much, but it does mean that if we're dealing with planetary-sized things, the one force of gravity won't cut it. Now, by the way, we're just using planets as a quick example. We are going to be doing a lot smaller things, but I think a planet is a good place to start because it's well, it's kind of the famous example. All right, so let's think about our planet here. In fact, we are going to imagine that we are have a cannon, but we have the cannon here on top of a hill. So here's our cannon, and this cannon is going to shoot a cannonball, and this cannonball will, follow the rules of projectile motion, just like we've done. And the stronger and stronger we shoot this cannonball, the further and further it goes. In fact, you could imagine that if we were shot it strong enough, we could get it to go pretty far, right? Now, our parabolas stop really looking like parabolas because the force of gravity is no longer just in one direction. The force of gravity is changing direction along with the surface of the Earth here because the force of gravity is always pointed to the center of the Earth. That means our projectile motion model won't work anymore. It's not going to cut it. If gravity is changing directions, that means that we can't split everything into a nice horizontal and vertical. We're going to have to use a different model. All right, so let's do this one more time. One more little planet here. This is a famous thought experiment from Isaac Newton. Now, why is it famous? I don't know, because it actually was the first time, well, there's a really key insight here. So again, we'll do some hilltop. We have a cannon sitting on a hill, and this cannon is going to shoot a cannonball perfectly horizontally for this moment, right? So the cannonball being fired out here is moving perfectly to the right. I'm going to try to keep the cannonball always yellow, the cannonball's velocity always orange. We've talked about how, well, if we shoot it hard enough, we can get it to land different places. Could you imagine that maybe we could get it to go, oh, I don't know. Do you think you could hit it here? I mean, you have to shoot it pretty hard, right? Do you think you could keep going and get it maybe over here? I mean, do you think there's a path that we could take that gets it all the way around here? I mean, don't get me wrong, it would have to be going pretty fast. Well, what Newton had the idea of is maybe if you do it just right, oops, maybe if you do it just right, you can actually get it to go all the way around the planet. Now it's not perfect, but that'll work. His thought was that if you shoot the cannonball fast enough, you can get it to go all the way around and come back and never hit the ground once. And in fact, if you get the cannon out of the way fast enough, well, if you get the cannon out of the way fast enough, it just would keep going, wouldn't it? Because the cannonball's in the same position it was in before. So here it's going like that. Ooh. All right, let me mess with my layers here, make it more visible. So here, our cannonball. Here's our cannonball. Let's do a different color. That yellow is not working. So here, our cannonball is on this path, going this way. Here, our cannonball is on this path, and it's going this way. Here, our cannonball is going on a path, and it's going this way. Now, this just keeps going for the whole time around the path, right? And what Newton got famous for was realizing, like, people were pretty happy with projectile motion. They were able to figure out, oh yeah, things just fall. You know, Galileo was doing his dropping stuff off the Tower of Pisa and all that fun stuff. But what Newton's really famous for is being the first person to realize, that the same thing that does projectile motion could also account for orbits. See, could this be the moon? Could the moon be traveling around the Earth, falling to the Earth? Falling, just like the cannonball is, but just be moving so fast that it never quite hits. That it almost just keeps overshooting it and just goes around in this perfect circle. We have satellites that do this. We have space stations that do this. What Newton got famous for was realizing that to account for orbit, you don't need anything new. Your old projectile motion stuff will actually count for orbit. Now, mathematically, we're going to need a new model. But let's start thinking about that here. All right, we're just going to define a few terms at this point. These terms will apply to any circular motion here. So in fact, this motion here is in a perfect circle. And our math is only going to really be good enough for perfect circles. Now, in real life, I don't think any orbits are perfectly circular. A lot of them are pretty close, though. So we are going to be generalizing just a bit. So we're going to be looking at circular motion. And let's just define a few terms. So first off, circular motion is usually defined by a few things. First off, we do have some sort of center, and we have some distance from the center to the path. We call this distance the orbital radius, or the radius in this case. Orbital is only when you're dealing with orbit. We'll be dealing with a lot of things that aren't orbit. So this is the radius, and the radius would we usually give the symbol r. It's just the distance from the path to the center of the circle. Probably not anything too crazy here. Now keep in mind, what if you want to know the entire length of the path? Well, the length of the entire circular path will just be 2 times pi times r. So this is the length of one revolution. Oops, if I can spell correctly. Hey, I can just press this button. By the way, if you ever want to cringe out of your mind, just watch your own YouTube videos. It's insane. If you want to know how far you have to go, it's just 2 times pi times r. You guys have done that math. There are a few other things you need to know. The amount of time it takes to do the path once. Oops. This is called the period. This is the time for one go around once. So let's see if you can figure this out. How do you think you find the speed? So the speed will be just the total distance traveled divided by the amount of time it takes for you to go around. Now, depending on the context, you could call this the orbital speed, the radial speed. We'll just call this the speed for right now. So the total distance traveled, which is 2 pi r, divided by the amount of time it takes to go around the period t. Now, I do want to point out we have to use the term speed here. And why? Because remember, speed, it doesn't matter what direction you're going. Why can't we use velocity? Well, you see this velocity? This velocity will have the same size as the speed, but see how that velocity is different than that velocity? And it's different than that velocity, and it's different than that velocity. See how the velocity is changing the entire time? So we never actually know what exact direction it's going, but there are a few things you need to know. The velocity is always tangent to the circle, to the path. So I'm assuming you've used the word tangent before. It's the line that just touches the edge of the circle and moves on. Our velocity will always be tangent to that circle. All right, everyone. So this whole orbit thing, we will do a little bit of orbital stuff, not a ton, but it's just a good introduction to these ideas that circular motion does seem to be possible. We see it all the time. And so we need another model to do it. Projectile motion won't cut it because projectile motion requires just one direction of acceleration. Well, here our acceleration is going to be changing all over the place. Oh, sorry. One more thing. This is actually probably the most important one too. I'm glad I didn't totally forget it. So you see here, we said that the force of gravity here was pointing this direction, whereas the force of gravity here is pointing this direction. The force of gravity here is pointing this direction. But everywhere where we put this ball, The force of gravity is in a different direction. But what do all those directions have in common? They're all pointing towards the center of this circle. So we have a name for this. Whenever there's a force pointing towards the center of that circular path, we call this a centripetal force. This is however much, this is the force pointing, the force acting on the object that is always oriented towards the center of the circular path. So let's write this down. The force acting. I put these grids in here to hopefully help my handwriting. Actually do seem to be slightly helping, but I'll let you be the judge of that. The force acting on an object, causing it to follow a circular path. It always points towards the center of the circle. Centripetal force is not a type of force. It's just it's like net force, right? It's just a way of describing force that just tells us about the direction. So for example, in this case, our centripetal force here is gravity. But later in the lab, you're actually going to be watching, the centripetal force will be tension, but you can also have centripetal forces that are normal forces or magnetic forces or whatever. The original models of the atom used some sort of Coulombic electronic force to try to hold the electrons to the protons and all that. But centripetal is always just describing how the force points towards the center of the path. It's not a particular type of force. All right, so your lab that you're going to be working on is going to be trying to see how all these things are related. How is the radius? How is the force? How are these periods? How are these speeds? How are they all connected to one another? Again, this is tricky. This is probably the hardest lab we do, and that's with me there. Doing it online is going to be a little ugly. That said, I actually really like the lab, the website that we're going to be using. I think it's about as good of a website I've ever seen for something like this. And it's way better than anything that I could have made in the classroom. Honestly, you're getting probably a better experience for this on this website than you would be from me in the classroom. All right, so go ahead, take a look at this, work on the lab. There's no time limit on this. You're welcome to ask me questions about this anytime you want. Drop by the Discord, send me stuff in the classroom, shoot me an email. And then probably this Friday, I'll start posting evidence assignments for this and maybe some practice assignments for this as well. And I'll also do a wrap-up video where we wrap up the entire model. All right, everyone, have yourself a great day.